So we are ready for our next category, which is Technical Innovation of the Year. And to present this category, we have Jamal Rostami, ITA Vice-President. Jamal, please.
Good morning, everyone. Andres, thanks for managing the session. I hope you had good refreshment and ready to go for the next session. I'm pleased to actually share this one. It's close to my heart. It's innovation, which is actually a window of what is to come. It's always nice to see what is the technology coming up our way. Before I introduce the contenders here, I have to explain something. There are a lot of entries for any of these categories. The ones that you see here are the ones that are finalists, meaning that they have gone through the screening. So it's important to realize that there are more, entries made into awards, but these are the ones that have been selected to go forward. Therefore, every single one of them are worthy of acknowledgement. So we have 3 participants in this category that are finalists. One is Advanced Tunneling Assistance System, presented by Alberto Flor and Andreas. Are they here? Alberto Flor? They're here. All right. The next category is this cutter wear sensor package and TBM monitoring system that is represented by Mr. Kim Jong-woo. Please join me on stage. And the third one is mirror tunneling AI. So we are actually entering the world of AI. There you go. Federico Foria. Andrea. Here's the remote. Welcome. So, before we start the presentation, I would like to ask you to introduce yourself and your, role in the project. Please go ahead.
Can you hear me? Yes. My name is Andrea Oss, and I'm from Sistra Italian branch. And together, my colleague Alberto Flor, we present the innovation called ATAS. This means Advanced Tunneling Assistance System. It was inspired by ADAS automotive principle, and the aim is to bring up an automation to the TBM excavation processes, increasing safety and real-time risk mitigation.
Good morning, everyone. I'm so honored to be here. I'm Alberto Flor. I'm a data scientist and part of the Research and Development Department of Sistra, Italy.
Buongiorno. Good morning. My name is Jung-Ju Kim from South Korea. I'm very happy and honored in this room, and I would like to express my respect and congratulations other finalists. KEPCO, my company, is the utility corporation that supply high quality of electricity power to South Korea people. This project was started to ensuring the safety of workers in single TBM chamber environment in accordance with the new safety regulation in South Korea. Thank you.
Nice to meet you. It's a great honor to take this opportunity to introduce our technology. We are a repair and manufacturer of TBM equipment in Korea, and we have proceeded with the structural design of this project. Thank you.
All right, thank you. Go ahead.
Welcome, thank you. And I'm Federico Foria. I'm head of research and development and head of geotechnics, geology and hydraulics department in ETS, which is a civil engineering company. And today I will present Mirror Tunnel AI, which is an assistant for the vulnerability assessment of tunnel structures.
All right, thank you so much. With that, let's move on with the presentations and see.
TAS, Advanced Tunneling Assistance System. ATAS, a trademark of Sistra, is an innovative platform that leverages real-time data, consolidated engineering methodologies, and artificial intelligence to assist during tunnel boring machine excavation. The platform translates concepts of advanced driver assistance systems from the automotive industry to the tunneling field. ATAS' main goal is to enhance safety with real-time updates on soil conditions, facilitating project adjustments and risk management. The Advanced Tunneling Assistance System is the result of a collaborative effort by a team of specialists at Sistra, Italy, each contributing their diverse backgrounds and experiences. Together, this dynamic team has pooled their expertise and insights from past experiences to create a platform that enhances safety, efficiency, and predictability in underground construction. In the automotive industry, Advanced Driver Assistance Systems, ADAS, is already reality, with constant monitoring and support to the driver. The sensors on vehicles stream an elaborate terabytes of data each day. Introducing the Advanced Tunneling Assistance System, or ATAS. Inspired by the automotive industry's ADAS, ATAS acts as a digital co-pilot, harnessing real-time machine data and cutting-edge technology to provide an assistance in tunneling, equivalent to a level between 2 and 3 of ADAS. The parallelism between ADAS and ATAS has been brought forward both in the way the machine can be controlled, and in the type of safety and risk mitigation aimed to obtain. ATAS orchestrates a symphony of data, continuously gathering and interpreting information from the TBM's sensors, surface sensors, and in advanced geo-investigations. Sampling is performed continuously on a timescale of seconds, generating gigabytes of data stored daily. ATAS begins with the initial design, storing and keeping all design data and calculations as guideline. Once excavation starts, ATAS continuously compares real-time data against the initial geological model. By analyzing TBM parameters, ATAS performs real-time soil characterization and compares it with design assumptions. Discrepancies are assessed for risk, aiding in the definition of new operational parameters. ATAS employs multiple methods for soil characterization by calculating parameters that correlate to the soil lithology. Thrust analysis derives the friction coefficient between soil and shield. Torque analysis estimates the soil's equivalent friction angle. Belt scale measurements indicate soil density variations. Pressure discharge analysis reveals soil permeability. After a training period, these equivalent soil parameters are used in an unsupervised machine learning clustering algorithm to automatically classify excavation areas according to different geological scenarios. Furthermore, ATAS can forecast soil conditions during tunneling, employing long short-term memory networks to predict the soil parameters. With a refined understanding of the subsurface, ATAS employs a combination of analytical models, FEM calculations, and machine learning to predict potential ground movements. Analytical estimations are continuously updated with real-time data. FEM models compute settlements for different face pressure values. Machine learning predicts settlements with progressive retraining. The final settlement forecast is a weighted combination of these methods, continuously refined against monitoring data. The system workflow operates in a continuous cycle for each excavated ring. TBM parameters are input, soil characterization is performed, and settlements are calculated. If settlements are within thresholds, the process iterates with the existing parameters, otherwise new TBM parameters are generated for the next ring. Advanced Tunneling Assistance System provides timely alerts, suggests operational adjustments, and aids in decision-making. It employs state-of-the-art artificial intelligence techniques such as K-means unsupervised clustering, stochastic gradient descent regressor with incremental learning, retraining, and long short-term memory recurrent neural networks. ATAS stands on the shoulders of giants, building upon decades of tunneling knowledge and experience. It leverages cutting-edge technology and established knowledge to significantly accelerate analysis and decision-making processes. ATAS has already proven its value in real-world applications. In the Wuch Railway project, complex and variable geology posed a significant challenge. The railway excavation was conducted in urban environment with shallow overburden, and it was characterized by changing geology with sands, clays, water table and interaction with very old buildings. ITAS provided crucial insights, enabling the tunneling team to navigate uncertainties and optimize operations, ultimately contributing to the project's success. Following this successful implementation, ITAS is being applied in other countries where Systra operates as a mass transportation system engineering firm, further increasing the system's training data. In the picture on the left, the ITAS characterization is compared to design expectation. The picture on the right shows the three methods for settlement prediction during excavation: analytical formulation, finite elements and machine learning. The dots represent the measured maximum surface settlement. The video shows an excerpt of the excavation, featuring both the real-time soil characterization, compared with the design characterization, and the prediction of settlement, compared to data from monitoring instruments on the surface. ITAS combines in a single tool real-time data analysis, soil characterization and settlement calculation. By monitoring and modeling the information predictively, it helps to identify and mitigate risks, ultimately enhancing safety, and it will be extended to other types of TBM machines. ITAS ideas stems from the automotive industry and provides a level of automation in between ADAS level 2 and 3. Advanced Tunneling Assistance System collects and analyzes a vast amount of data from the excavation site, using advanced algorithms to support faster and more effective operational decisions. This platform is part of Systra's commitment to digital transformation for a more sustainable world.
Yeah, we will never cease to be amazed by human ingenuity. This is really amazing. With that in mind, let's go to the next presentation, and we'll come back to ask some questions from the participants.
KEPCO Research Institute is at the forefront of electric power technology innovation. Among its teams, the Power Structure Design Project team conducts R&D in tower and cable tunnel design and construction to ensure a reliable electricity supply. KEPRI is leading the research and development of disc cutter wear sensors with the participation of various institutions such as Bugyang National University, TNM, HBC, and Duna Information Technology. For cities and energy, for the environment and safety, future energy transmission technology. At the very core is undergrounding of transmission lines through power cable tunnels. KEPCO has safely constructed over 200 kilometers of cable tunnels using the TBM method, with the safety of tunnel workers during construction as its highest priority. The change in magnetic flux density due to the volume change of the disc cutter ring can be measured using a magnetic displacer sensor. The variation in the magnetic field between the permanent magnet and the disc cutter ring can be converted into the amount of wear. The disc cutter wear sensor package includes a magnetic sensor, a power supply battery, a wireless communication module, a control board, and an external casing. The wear measurement accuracy can be maintained at over 90% in various excavation environments, and the disc cutter wear limit can be measured up to 35 millimeters. As a technological innovation, the Zigbee wireless communication module and battery system were implemented to overcome the challenges of wired connections in continuously rotating TBM cutter heads within excavation environments. To facilitate easy and quick replacement of the disc cutter wear sensor package, the existing disc cutter wedge bolts were utilized. Each package can be replaced within 3 minutes without any additional work. Additionally, it has been developed to accommodate various installation methods for the different holder types of the disc cutter. Basic applicability tests have been completed for various sensor candidates. Sensor tests were conducted in air, water, slurry, and soil environments, and the optimal sensor was selected for the 17-inch disc cutter. The developed sensor has completed full-scale validation tests under artificial rock conditions using a 3.6-meter EPB TBM. Its performance was confirmed at concrete strengths of 27 megapascal and 60 megapascal, with a maximum thrust of 3,000 kilonewton and a rotation speed of 6.0 RPM. Additionally, tests were performed to verify the differences in sensor measurement data between normal and uneven wear conditions, which were used in the development of the algorithm. By analyzing the data collected from the wear sensor for normal and uneven wear, it can be observed that the uneven wear data exhibits distinctive characteristics in the voltage values. This difference will be used to classify the wear conditions. A convolution neural network model was employed to classify the wear conditions of the disc cutter. The CNN demonstrated exceptional performance, achieving an accuracy of 99% in distinguishing between uneven wear and normal wear by extracting patterns from the time series data through filters. Additionally, the life prediction model utilized a convolutional recurrent neural network, which combines the feature extraction capabilities of CNNs with the time series processing abilities of recurrent neural networks. This combination makes it well suited for learning wear trends and predicting the remaining lifespan. Various TBMs and PLCs used in cable tunnel construction have been developed to acquire real-time data using industrial communication protocols. Modbus, TCP/IP, OPC-UA, and Zigbee protocols were utilized to enable communication between the PLC and the wear sensor. 2 PLC communication boxes were installed within the TBM to establish an efficient data transmission and reception system. Validation has been successfully completed in the Sejong area, the Ansung Pyeontaek area, and at the TBM Testing Center. The TBM monitoring system digitizes the construction status of cable tunnel projects, ensuring construction stability and improving management efficiency. The transmitted data is processed and visualized for display in the construction management system, enabling project managers to easily oversee the construction site. The main screen of the monitoring system provides an overview of the construction status, potential risks, and measurement data at a glance. It includes features for real-time TBM machine data monitoring, optimal operation recommendations, excavation volume management, routine measurement tracking, ground settlement prediction management, and excavation tool wear management. Based on the theoretical equations derived from three-dimensional numerical analysis results, the system predicts the future final surface settlement at the current TBM location. The system calculates and provides surface settlement estimates based on 4 influencing factors: TBM face pressure, TBM over-excavation, TBM backfill grouting, and groundwater level decline. This technology is poised for application in the construction of small-diameter TBMs in single-chamber projects. When implemented in a 29-kilometer-long, 500-kilovolt HVDC cable tunnels, it is expected to significantly enhance construction safety and excavation efficiency. By reducing unnecessary chamber operations, the future minimizes the exposure of tunnel workers to hazardous environments. Furthermore, it can decrease TBM downtime by over 40 days for a 3-kilometer power duct tunnel project, resulting in an estimated economic benefit of approximately 230 million Korean won per site.
This was pretty amazing, and again, it's pretty much out of the world, and it's showing us what's coming in the future. So again, we'll have time for discussion, so let's move on to the next presenter. And
Yes, I will have a few slides, a video, and then a few slides. So, okay. Hello everyone. This could seem like a marketing slide, but that's not. It's just a reminder for me that first of all, I want to thank all the people that make possible for me to be here to present. I'm just, let's say, a representative of all of this work, because today I will briefly introduce you a work of more or less 10 years of the history of the company, history on working mainly on existing infrastructure and existing tunnels, of more than 2,000 kilometers of infrastructure surveyed and assessed, and with all the engineering know-how which is behind all this work. So this was important to say because I will talk a lot about AI afterwards. So, but this is the premise of all the AI things that I will say later on. And for doing this, we invest a lot in research and development. Here today with me, there is also the coordinator for the development of the product, Mario Calicchio, is in the audience. So I want to give a special thanks to him because he represents the development team behind this work. This is also really brief because this project is part of a vision that we have, which infrastructure is a social value. I think this is undeniable. So the infrastructure links markets, economy, environments, people, so it's a social value, but our infrastructure are aging. They are like old people, I like to say, because I'm quite young, so I see them like my grandmother or my grandfather. So we need to ensure them innovation in order to make it possible for us to use them and to exploit their expertise. Now we will have a video. I will not talk all the time. We have a video that will present Tunnel AI, and then just 2 slides just to highlight some points that maybe in the video cannot transfer, but maybe I will try to do better. So. Okay, it was a nice video indeed, so I will just make a focus on a few points. So what we are talking about here, as you can see in the video, we are talking about, we have a system for multidimensional survey and inspection of the tunnels, and from the data coming from this system, which is called ITA, we then developed in a couple of years the system that we are introducing today. So the system basically is a series of algorithms and a software in the end, which you can see the interface for the assisted assessment of data for the vulnerability analysis of tunnel structure, of existing tunnel structure. So this was shown really well in the video also, which is the process that we are going on for doing this. I was just to pin a really little focus on this nice infographic on the part that you have on the bottom right, because we talk a lot about artificial intelligence, but I think it's also important to remind us that we have in almost in almost all the parts of the world, but especially in Europe, we will have a framework that will become compliance in the coming year, which is the AI Act, the Artificial Intelligence Act, that ask us to be compliant in a lot of things. And all the applications that we are seeing today are applications in infrastructure. So for the AI Act, they are high-risk applications. So in high risk, you need to be compliant with a lot of things. So you need to explain privacy, you need to explain cybersecurity. The AI needs to be explicable in some way. You need to have a risk management framework for the implementation of the AI. And this is something that I'm really glad to share, because Tunnel AI actually is compliance in the service with all the main hotspots that the AI Act is asking. So the one that you were seeing also in the video. This is just a frame from the interface. It's just to show what in the video. We have the data, then we had the pre-assessment with the AI, then we had the operator that was interfacing with the AI, adjusting the parameter, asking for additional labeling of the defects that you were seeing in the video, or asking for additional information, and then in the end the data are validated. So what is the result? Is in an open format, exchangeable format, a digital model of the asset management of a tunnel. So what the AI brings out is a digital model of the informative model for the vulnerability assessment. So we have geometries and we have information out of it. And this is the last one, is just to show that especially when we talk about this kind of implementation, we need to focus on sustainability the same, because all this process was analyzed from the sustainability point of view. So in the end, we said, okay, we are performing really well with the mobile survey, with all the technology and so on. So compared to baseline calculated, but then we have a lot of back office time that we need to, in some way, can be more efficient. So this was the basic for the implementation of Tunnel AI. So sustainability is not just something that we calculate and we come out and say, okay, now it's time to do some sustainability, but sustainability is part of the whole process. So it's in the beginning, it's throughout the process, and it's in the end of the process. And so this is showing with Tunnel AI, we reduce basically the back office part with, I think, some good results. What is shown, and in the sustainability, there is also the safety part, because there is a safety part on site, which is reduced thanks to the essentially the mobile technologies, and also for the security of data and the work of the operators in back office. Thank you so much.
Okay, thank you so much. As tunnelers, we're always looking into the light at the end of the tunnel, right? This is the brighter future that's coming our way, and I'm glad that we are seeing it a lot faster than we thought. So going back to the project and entries in the ATAS system, verifying the geology is a really monumental task. I mean, have you been able to actually verify? You showed that in your video that you could verify the predictions versus the reality. How did that work? I mean, is it something that you have actually done and you're comfortable with, or is it something under development?
Well, thank you for the question. Sure. So a point like investigation, I'm not really sure we did everywhere, but somewhere we had some feedback on our characterization. The main idea, and as you said, is under development. It's the main idea behind everything is TPM parameters, or mechanical feedback when the machine is in contact with a rock or the soil, encode some part of information of the real environment to the TPM. So this is an assumption, maybe a fairly good assumption, and then there is a learning period. Even if you don't use machine learning, there's still a learning curve when you try to see if how the trend of the quantities you calculate compare with the real case. So to answer your question, there is not like step-by-step comparison, but you can see that some trends lead to certain consequences. So, and after a while, you are pretty confident that the system works. If your question is there a need to a stricter way to prove that? Yes, of course, but we didn't apply it in many cases. We actually applied it completely in one case. It still is based on research on other excavations, but like methodically, in this way, we did it just once. So, yes, did it answer?
No, a big issue in Luce project was the strictly alternance of sandy and clay soils. So it was another difficult issue, no, to be faced during the excavation and during the application of this innovation. And low overburden, very low overburden context in approximately 1 diameter, and high groundwater table. So in urban environment with ancient buildings. So it's a very, very critical application for this innovation.
All right. In your presentation, you referred to unsupervised training of the program. Why unsupervised? You could actually do intermediate step.
It's just, I said unsupervised. We applied some algorithm, but it's more like the output of the different quantities that we calculate, we correlate with some, in this case, it was the percentage of clay or sandy soil. And after a while, we said, okay, we can train a new algorithm that clusters the output of all the calculations. So maybe we have 4 quantities, but like you can develop more. And if 3 says that it's all sand and 1 says that it's all clay, you have to give a weight to which method works best in that context. So we train a, let's say, additional algorithm that just clusters in the hyperspace the point that come from the calculated quantities. So it's there is a layer intermediate, which is the calculated quantities we mentioned, and then we just clusterize them in the, okay. We find the centroid of the points, and then we assign our weight.
Sure. Very good. And perhaps final question. I'm assuming that you're monitoring operator behavior as far as how they operate the machine to do your, essentially train your system. Have you had the situation where the operator behaviors are different relative to the same ground, and how do you actually mitigate that? How do you reconcile that into the program?
Can you repeat the question? Sorry, I may have...
So your system is essentially monitoring TVM operation, right? And I'm assuming that your sensory system is monitoring how the operator reacts to the ground. So the question is, if the operators behave different in the same ground, how do you reconcile that? How does your program choose which operator did better?
So right now, the idea is to give a recommendation on how to operate given the parameters at that moment. So we take into account even slightly the choices that are made, and they turn, like they are input again to our process. So, and then we just, the output says, if you go on like this, it's gonna turn bad. So it's just a recommendation. And we take into account everything, all the parameters, even those that are man-operated. Of course, there is we are not in a totally like natural scenario. We have the human impact in the data. They are dirtied by the operation of the operator. So but right now, we use that as it is an input from the outside.
Thank you so much. It's still amazing. Oh, okay.
No, we have talked about mainly about the geological condition, but the other issue was the settlements prediction. It was very important, and we have done this combining various technical, analytical techniques, FEM, 2D and 3D models, and machine learning techniques from the surface targets in order to combine this technique and to provide a reliable prediction.
Amazing. Let's give him a round of applause. Okay, going to the next presentation about the sensor system for TBM and, of course, for cutter wear. All of us know that this is a very critical issue because intervention and inspection of the disc cutters is very risky. And if you can minimize it, it's pretty amazing. So what's the main principle behind your disc cutter sensor?
Professor, thank you for the question. For clear information, I wrote something. The disc cutter sensor operates based on the principle of magnetic sensing. Variation in the volume of steel ring in the disc cutter induced change in the magnetic field between the sensor and disc cutter ring. These magnetic field fluctuations are detected as change in the Hall voltage on the sensor's PCB, utilizing the Hall effect. The measured Hall voltage variation are then precise correlation to the wear of the disc cutter. This methodology constitutes the core of our measurement system.
Okay. Thanks. And what's the current development level? Where do you think you're going to go next?
Yeah, we performed the experiment under various conditions using the both mini disc cutters and the 70 inches disc cutters. We analyzed the change in the sensor's Hall voltage in the environment such as water, mud, and slurry. Additionally, we artificially generate the wear on the disc cutter using a grinder to verify the measurement calibrations. We carried out full-scale excavation tests on the 3.6 meter class EPB-TBMs. Evaluation the performance of the sensor, network, and durability under the actual excavation condition. And moving forward, we plan to execute the comprehensive validation to assess the systems to maintain the reliable performance over the excavation distance approximately 250 meters or more using the 3.6 slurry TBM. Furthermore, we are preparing to carry out the advanced performance verification with the accessible cutter tube over the 15-meter slurry TBM in the near future. Thank you.
And the last question here, what do you do with this measurement? What can be done with it? And also, how many of the cutters do you anticipate to instrument per cutter head?
The goal is to provide the water mount of the sensor to the operators so that they can determine the remaining life and replacement cycle of the disc cutters. Additionally, an algorithm has been developed to detect the uneven wear patterns by training a deep learning model on the measurement data. In general, sensors are not required to be installed on the disc cutter. Sensors are installed at the beginning and middle and end of the face and gauge disc cutters, allowing to the lifespan of the disc cutter without sensor to be the estimate. The decision was made by consideration both economical aspect on the sensors and the delay time associated with their installations. Thank you so much.
All right, thank you. Actually, the video was more extensive, so you have done more with the data and TBM monitoring than what you actually showed here. So kudos, very good job.
Yeah, thank you very much.
Round of applause for them.
Thank you very much.
And moving on to AI, that's a really big field and it's a growing field. So I was wondering if you are planning to integrate your systems with the BIM, BIM, or with the digital twin.
Yeah, that's really interesting question. So actually, from the informative modeling point of view. So let's talk first about BIM in general, like also, I don't know, not building information body, like better information modeling. And this is like with an informative model approach, because the AI is extracting an informative model, which is an open format. So then it's exchangeable with other software based on a BIM approach, or can be integrated in asset management platform. And then inside you have geometries, can calculate it, and you have information related to this geometry. So it's a compliance with the international standard regarding informative models. Regarding direct input inside BIM models, that can be done in a lot of different ways. Then it starts becoming a texture or a patch inside the models, or can be extracted like diagnostic output from a portion of entire type of structures. So it's completely considered that it's open format, then it's spatialized, there is auto-rectification behind, then it's easily integratable in a lot of approaches.
Oh, okay. All right. Also, you're trying to automate the inspection. I guess ultimately that's the goal, right? In your video, you showed that you're using interferometry or optical. How are you planning to actually integrate multi-sensory system or multi-mode, even with the people and individual going and checking something? How do you integrate all of that into the same system?
Yeah. Here we have two steps, an acquisition point of view and an elaboration point of view. From the acquisition point of view, we are already quite far, because we have the system that was shown in the image, which is called Archita, is already a multidimensional mobile mapping system. So it means that we can acquire with that system photogrammetry, so photo, 3D point cloud, ground penetrating radar for the bottom, and also ground penetrating radar for the lining with an automatic arms that works specifically for this part, and also thermal images. So these are all the basic instruments that are today more or less standard to have a non-destructive acquisition inside the tunnel inspection, and they are already, from the hardware point of view, they are already integrated on that part. So acquisition is already quite far. So we can improve, but is already quite far. From the elaboration point of view, AI now works really well on the photogrammetric part, so the one that was showing here, but basically our program here is to work with this approach with all the hardware that is already integrated we acquire, and making this assistant the assistant of all the data, the non-destructive data that we acquire for our system. So in a future, you can relate with the system, but also with the ground penetrating radar data and thermal data and so on.
And with your systems, apparently all the sensory systems are superficial, essentially checking the surface. Can you check the voids or issues behind, or how accurate is your GPR to validate what's happening behind the lining?
I will not make a sorcerer or like a magician, because I'm then a tunneling person in the end. So we know this can vary a lot depending on condition of the structure, type of structure, geological conditions, water presence, and so on. So considering that we already know all of this behind, I will say that, for instance, all the vulnerability, we call it superficial vulnerability and deep vulnerability. So we are focused a lot on superficial vulnerability, but we also have information in the models regarding deep vulnerability, which is coming from basically the thermal images, especially for the water part, and then the ground penetrating radar. And the ground penetrating radar is a mobile ground penetrating radar, so we're not here to. I'm not selling ground penetrating radars, so I don't need to let's say sell dreams about mobile ground penetrating radars. But they are quite useful, because if you put them with the thermal images, the evidence that you have, and also especially on not the ordinary, especially the principal inspection and so on, you have also already performed tests and other elements that you can back up the information on. So in general, With this system, we did now like 100 kilometers of tunnels in less than 10 months now, and especially with the Italian Road Authority, which endorsed our application. Yeah, so I also take the opportunity to thank them and ANAS, and so in all the tunnels that we did, this worked well, backupping all the information together. This system can do it because in the image you can see on the left that you can put all the information, you can overlap all the information, and then you can relate the information in the model.
All right, well, actually, kudos to you again, because you mentioned that all tunnels are like grandma and grandpa. So we can tell our doctor friends that we are ahead of them. We are rejuvenating the old tunnels, but they cannot rejuvenate us. So kudos to you. A round of applause for everybody here. And best of luck to you. We'll see who is the actual final winner this afternoon, although you're all winners by being on the stage. Thank you.
Thank you.